Hello and welcome back to this series of videos where together we learn the basics of Lean in order to write simple maths proofs. We're now a good way into our journey, and last time we started what we called part 3, where we're going to be learning and practicing how to apply definitions and lemmas. So in the last video we looked at applying the definition of odd and even to prove that something was even or odd. Today we're going to be looking at an actual lemma, a bit of kind of mathematical knowledge that's built into Lean, and seeing how we can use that to aid our own proofs. And this is a really common thing to do, so it'll be the start of many journeys. So it's a really kind of important step in our journey. So just to clarify, there's lots of mathematical knowledge that mathematicians use in their proofs without having to prove everything from scratch. Lean does contain a lot of those ideas, obviously proved, otherwise we wouldn't be able to include them in Lean, and they can be used, and they're growing over time as well. It's quite an impressive number actually if you want to go online and see what the current state is, but there's thousands and thousands of theorems and lemmas now in Lean. We made a distinction last time with definitions. Definitions are just that, definitions. They don't need to be proven as long as they're consistent. But lemmas and theorems are things which do need to be justified. So within Lean, somebody has justified them. The proofs are within Lean, but we don't need to prove them to use them. We just need to use them by their name effectively. So let's look at our really simple one just to get started. So we've got a task which is again really simple. Given a natural number n, which is less than 5, so n is less than 5, we want to show that it does not equal 5. Now, you and I can look at that and say, well, obviously that's true. But we are encouraging ourselves to think a little bit at the next level of detail to see, well, if somebody's not convinced, how could we do that? Again, we could go all the way back to the axioms, but we're not going to. We're going to use a lemma. Now, the idea is not really to explore this idea of whether, if a number is less than 5, it's not 5. The idea today is to see how we can find a lemma to use and see how it is kind of written in code and how we can apply it. That's the main kind of idea. So the maths problem is chosen not to be overly complicated because we don't want to get distracted. Just some terminology. We say that this is a disequality, whereas things like less than, more than, less than or equal to, more than or equal to, in school we learned the word inequality and use that quite a lot, but for some reason we didn't really learn the word disequality, and that's specifically for when something does not equal something. In my mind, it feels like this is an inequality, but I think it's cleaner to say these things are inequalities, and this is definitely a disequality. So we're going to use some common knowledge. That's what a lemma will encode. That if a and b are natural numbers, and if a is less than b, then a does not equal b. That's kind of common knowledge that we can think of as a small lemma and see how we can apply that to our problem. So let's draw a picture of that just to make that clearer. So if we say that there is this common knowledge that if there are two natural numbers a and b, if a is less than b, then we can conclude that a does not equal b. As we said, we could go all the way back to axioms to prove all this, but we're not going to. we're going to say that somebody has done all that work and proven this factoid, this lemma, and it's now ready for us to use. Somebody's done the work of proving it, and it's a useful little thing. In fact, it's so obvious that most of us do it in our heads, but that's we can think of it as a little lemma. So we have our own problem, which is n is less than 5, which matches this. And if we can prove that, then we can prove that n does not equal 5. So if we can prove this, then we've proven that. That's what implications do for us. If P implies Q, if we can prove P, then we can say Q is true. So by applying this lemma to our problem, that will help us get to that conclusion if we can show this is true. So let me draw another picture. So our problem was that we have a hypothesis. Oops, big writing. That's the hypothesis. We know that's true. Our proof objective is n does not equal 5. That's the proof objective. We want to get from here to here somehow. If there's a lemma which says that a less than b means a does not equal b, then we can make use of that by saying n is less than 5 means n does not equal 5. And if we can prove that, then we've proven that. And how do we prove that? Well, we're actually given that. There's not a lot of work to do. It's the hypothesis. Sometimes we might have to do a bit of work to get there, but with this example, it's given to us on our plate. So this is true because we're given it by hypothesis. Then that's true, and that's our proof objective. So that's how we're going to play it. So we've written this out in that detailed form again, which sounds, it looks a little bit laborious, but it helps us think ahead a little bit and do the right thinking, ready for writing a lean proof. So as always, good habit, write the hypothesis at the top, proof objective. Now this is the, sometimes we write definitions and hypotheses. Today we're going to also write the lemma we're going to use. So this is an existing lemma. It's existing. We're not going to justify it. Somebody's done the work already. We're going to steal their work, or rather stand on the shoulders of somebody else's work and use it. So somebody has proven this. They've done the hard work, and we're going to use that lemma. So by using this lemma, we can say, if we can prove the left-hand side, then we've got the right-hand side. So it's sufficient for us to prove n is less than 5 in order to prove that n does not equal 5. So it's a sufficient goal, this one, to prove this one. So for us that means n is less than 5. And how do we know that's true? Well, we're given it as a hypothesis, and therefore the right hand side is true. So n is less than 5 implies n does not equal 5 by the lemma. Phew, that was a lot of words, but as I say, it's mental training, getting us to think in a way that will help us write lean proofs. You can read this yourselves on the slides, they're all online, and you can also read the blog, which explains these ideas with more carefully chosen language. So again, I'm going to do a kind of a live coding today, because it might be sort of more engaging, and we can think out loud as we do it. So you could use the Visual Studio Code environment. It's quite convenient and nice, or you can use the online environment at live.leanlang.org, so you don't need to install anything. So we've imported a mathlib tactics, and we've made a statement of the thing we're trying to prove, the theorem we're trying to prove. So we've called it example because we don't need to give it a name. We've defined the variable type, so n is an integer. We have a hypothesis that n is less than 5. And our proof objective is n does not equal 5. So how do we proceed? So what we did in our maths proof was we applied a lemma that exists already. We need to find one in MathLib. Now, one of the things that is less than perfect in Lean is that finding the right lemma is not always super easy. It can be easy, if they're very famous lemmas, but sometimes it can take a while to find it, or you need to ask people who know. Some of them have a naming convention which can help you identify it, but I have to admit it's not an ideal situation. Maybe in future that will be improved. There are some search engines as well which are trying to help, but again they're not perfect. So I'm going to tell you what the lemma is. And the lemma has a name. It's not equal of less than. And a lot of the lemmas that you'll see will look like that naming scheme. What this means is not equal of or from less than. So we're trying to prove not equal from a less than. That's for now, that's the way to read it. It says of, but in my brain I think from. So not equal from less than. We'll talk about that in a second in more detail. So we apply a lemma. So we use the instruction apply. The Lean server has stopped. How can I restart it? Restart the server. Okay, so that's back. So let's look at the info view because that's always useful. At the end of the proof statement, the statement of the theorem we're trying to prove, let's have a look at what Lean thinks is going on. It knows that n is an integer, is a natural number. It knows about a hypothesis that n is less than 5. So that's the hypothesis, that's that one. And the proof objective is n does not equal 5. Perfect. After we've applied this lemma, let's see what happens. The goal has changed to n is less than 5. So look at it when I click at the start here. N does not equal 5 is the goal. If I click at the end, n is less than 5, so the goal has changed. We could have a calc section, I guess, but it seems like there's an opportunity that if the hypothesis is n is less than 5 and the goal is n is less than 5, we could apply the hypothesis, and that works. So applies lemmas and hypotheses. So we've seen the use of apply here. So that's new in today's video, this use of apply. And they are applied to the current goal. So let's step back again. At the start, the goal is n does not equal 5. After applying this lemma, which exists within MathLib, we've transformed the goal to n is less than 5. And we know that that was given to us by hypothesis h. We can just apply h and then job's done, no more goals, everything's proven. So we could finish there, perfect. However, I just want to say one more thing. Because this hypothesis exactly matches that goal, we can say exact. Now you might say, well, what's the benefit? If apply works, why do exact? And the reason is exact is stricter. Exact will only work if the applied lemma or hypothesis does exactly match the goal. If it doesn't, then it won't work. That's useful because it helps us find errors more easily. So because apply is less strict, if there was a misunderstanding somewhere, the apply might work, and we'd only run into trouble kind of further down the proof. Whereas here we do fully expect the goal to match the hypothesis. So if we assert it, and if it fails, that means we were wrong in our thinking somewhere. So it catches the error early. So being strict as you can be, in some ways it's good because it's kind of catches errors and misunderstandings up front sooner, which is a good thing. So apply will work, and exact, when it can work, you should try and use it. They're not interchangeable, so whenever we have exact, we can use apply, but whenever we have apply, we can't always use exact because there might not be an exact match. So that's it. That's today's example code. Let's see what else we were going to say about it. So you can read this yourself, download the slides if you want. Apply applies a lemma and usually results in a change in goal. It exists in MathLib, as so do thousands and thousands of other lemmas. I said earlier that it's not ideal, finding the right one, but the naming scheme can help. So it's useful to be able to read these. So this says not equal, from or of, less than. So we want to prove ultimately a not equal. That's our proof objective. From less than, which is kind of where we want to start from, and that's our hypothesis. That's useful. So we can prove the not equal goal by proving a less than goal. And the info view is really helpful to see those changes in goal. So it's useful to kind of compare the maths proof with this lean proof, just because there's some new ideas here. So the application of that lemma, apply any of LT, that corresponds to line 4 here. So we're saying that's a statement of the lemma, but it's the application. When we apply the lemma, by lemma 3, this is a sufficient goal. So even though our ultimate goal is a disequality, by that lemma, if we prove this, then we've got that. So the application of the lemma means that we just need to prove this left hand side. So that this line is what corresponds to the apply any of LT. And the final application or exact of the hypothesis is this line 5. So we're saying n is less than 5 because it's given to us as a hypothesis. So just being able to compare those two things is useful. Yes, we did talk about the difference between apply and exact. So, whenever you use apply, you can use apply whenever you use the exact, but not the other way around, and it's stricter. I won't talk through this again. You've seen that with the live coding demo. But again, to emphasize that the info view is really helpful to track that your goals are changing in the way you expect as you write the proof. Worth saying just a few short words about lemmas and theorems, mathematical jargon. Broadly speaking, lemmas are seen as kind of smaller, less important, whereas theorems are grander and possibly kind of important in changing our understanding of mathematics. So the bigger important things are called theorems, and the smaller, perhaps trivial things are called lemmas. The distinction isn't clean, and as far as lean goes, some things are called lemmas, some things are called theorems, but they work in the same way because they're just propositions that somebody else has proved that we can use. So, there's no real difference from our perspective. And as I said, it's not ideal trying to find the right ones, but quite a few do conform to that naming convention, and over time we'll get used to them. So don't worry for today, but in the coming videos we'll see more lemmas, and we'll be able to kind of recognize, that's what that means. And then you'll be able to say, well, I'm looking for a different lemma. Let me, you can probably guess what the name is. Before we go to the easy exercise, I'm just going to draw a picture just to kind of re-explain what that lemma did for us. So this lemma said A less than B implies A does not equal B. That was the lemma. If we wanted to ever get to A does not equal B, if that's where we wanted to get to, we're not thinking about where we're starting from yet. That's a question mark for now. You can see that this lemma kind of builds a stepping stone before that. So it gets us to this if we can prove this. Now this may or may not be useful. If it is, great. It means that by applying this lemma, all we need to do is prove this. So it's given us a step, and we just need to prove A is less than B. Now maybe there'll be other steps that we have to do, so that might not be the complete proof, but it kind of takes us to the penultimate one. Or actually, for much longer proofs, it may be that this lemma takes us from there to there, or allows us to get there from here, and this is actually kind of midway through a proof. So you don't need to think of them as necessarily always taking us to the very final overall proof objective. They can be stepping stones. But I drew this picture because the important thing here is, if we've got either an ultimate overall proof goal or an intermediate goal, partway through the proof, and if a lemma kind of matches where we're trying to get to, we can, it could be useful. I'm not saying it always is, but it could be if what it gives us is an easier thing to prove like that, then we've gone there. That's the picture I want you to kind of take away. That's what this lemma does. A lot of them will do that, not all of them, but a lot of them will. So let me reset the canvas. Essentially this one is of the form if P then Q. If we want to get to Q, if we can prove P, then we've got Q. So that's kind of what's happening. I wanted to draw that picture because all this talk of code, that big idea might have got lost. Overall, don't worry if that was a little bit too new. We're going to practice over the next few videos because it is important, the ability to apply lemmas. So we'll put in more practice. For the easy exercise, it's particularly easy, I guess, this time, because the task is almost the same. So we're going to prove n is not 5 for integer n, for natural number n, but this time we're given n is more than 5. So just to visualize that, with our example we had n is less than 5 and we wanted to prove n does not equal 5. For this exercise we're given n is more than 5 and we want to prove n does not equal 5. Now you and I can look at that and say, yep, obvious, but we want to write a lean proof. And in here we used a lemma that said A is less than b implies a does not equal b, and that was called not equal of less than. So not equal from less than, proving not equal by proving less than. So you can almost see there's lots of parallels here. What's the lemma we would probably try to use here? Well, it won't be a is less than. It's something that implies a does not equal b. Something that involves ab. It'll be this one, won't it? Because that's what's useful in this context. And can we guess the name? But it'll be of something, and we're trying to prove a not equals from. Is it less than, or is it greater than? That's probably the name of the lemma, any of gt. Let's try and do a search for it. So the official search engine from the Lean project is called Loogle. So let's try and put in the one we know about, any of less than, any of lt, and we'll find that. And it says, yep, found one definition matching it, and that's the explanation there. Let me make the thing a bit bigger. A is less than b implies a does not equal b. So that's the lemma that we used. For the exercise, we think it might be greater than. Let's see if that exists. Let's click find. Oh, it does. Found one definition. So any of gt, so b is less than a, or a is more than b, implies a does not equal b. So yeah, that works. So that does exist, and that's the one to use for the exercise. I wonder what happens if we click on it. Does that take us to the actual source code or the official documentation? Where is the one we were looking at? Any of lt and any of gt. Let's look at any of lt. Let's look at the source. Okay, probably don't need to read the source. But these signatures tell us that this lemma, or it's called a theorem here, has two parameters, a and b, and there's a hypothesis that a is less than b, and the output is the proposition that a does not equal b. So it's, we'll start to learn to read these things. Again, don't worry if that's too much for today, but we'll get practice in the coming videos. Fantastic. Well, that's exciting. We're on a new important part of our journey. So looking forward to getting some more practice in next time. See you next time. Bye.